Good day, everyone. I'm Zheng Qiang from HiSilicon Optical Electronics. Very glad to share our works. The title of my presentation is PAPR Constrained Digital Brain Emphasis for Short-Reach Coherent Systems with Transmitter Bandwidth Limitation. My presentation includes 4 parts. The introduction, the principle of the PAPR Constrained Digital Brain Emphasis, experiment and analysis, and conclusions. Let me start with a brief introduction to the backgrounds. As we know, optical modules for data center applications are evolving from 400G to 800G and 1.6T. And the coherent technology is a strong competitor from the IMDD technology. And for coherent optical modules, we need at least 100 gigabit up to 200 gigabit to satisfy the applications of 800G and 1.6T. And there will be several bandwidth limitation challenges. So we need the digital brain emphasis as the transmitter to compensate for the transmitter bandwidth limitation. But the DPE will increase the PAPR of the singular into the DAC and will result in the increasement of the quantization noise and nonlinearity. To get a better performance, the partial DPE is proposed, and the commonly used partial DPE can be expressed as this formula. We call it the sweeping alpha method. Here, H sub pre is the frequency response of the DPE, and C sub Tx is the frequency response of the transmitter. Alpha is an adjusting parameter that can control the amount of the precompensation. If we have more precompensation as the transmitter, we will get lower equalization enhanced noise as the receiver. And when we decrease the precompensation, we will get benefit in the condensation noise at the transmitter. And finally, the optimal digital brain emphasis is a trade-off between these two factors. This optimization considers only the noises of the system, but not the output power. We know that the output power is also a critical issue for the short-reach links because there is no amplifier in the link. So there is the problem. How can we find an optimal DPE for the short-reach links that considers both the noises and the output power? We know that all these factors, including the noises and the output power, are directly related to the PAPR of the singular after DPE. But when we try to use an optimization method to solve this problem, we find that the definition of the PAPR is hardly used because the singular X is a random process and we cannot exactly calculate the peak power. So we need to find another way to describe the PAPR of the singular. We know that most of the singulars has a Gaussian-like distribution, and the distribution of the singular's power is like this curve. It has a tailing, and this tailing is related to the PAPR of the singular to a certain extent. For example, if we have two singulars, they have the same average power, but one singular has a long tailing and another has a short tailing. We can think that the singular with a short tailing has a lower PAPR. And under this idea, we can constrain the PAPR of the singular after DPE by setting an upper bound to the probability of the tailing. In time domain, the singular after the DPE is a convolution of the input singular X and the DPE impulse response H sub pre. And the probability of the tailing can be expressed as this formula. It is the probability of X prime squared more than a constant C, and setting an upper bound to the tailing means that this probability should be less than a constant P. When we assume that the singular X is a zero mean generalized stationary random process, and the DPE impulse response H sub pre has a finite power, we can use the Markov inequality and the Cauchy-Schwarz inequality to get this inequality. Here, the probability of the tailing will be less than a constant times the integral of the H sub pre squared. And this inequality can be used as a PAPR constraint. Then we consider a simplified system as shown in this figure. Here, only linear effects and linear compensations are considered. The original singular is processed by the transmitter side DSP and fed to the transmitter. After channel transmission, the signals are received by the receiver and processed by the receiver side DSP and get the final single Y. To be convenient, we consider all these factors in the frequency domain, and the PAPI constraint is added after the TX DSP. Here we transform the PAPI constraint from time domain to the frequency domain using the Wiener-Khinchin's theorem, and the constant before the integral is ignored. Here P prime is not constant, that has no influence on the results. And we need to consider fix the SNR after the channel transmission to make this problem solvable. Finally, the problem can be described as an constrained optimization problem. We need to minimize the mean square error of the final single Y, subject to the SNR constraint and the PAPR constraint. Using the Lagrange multiply method, we can get a solution as this formula. Here, PS and PN are the PSDs of the signal and noise. Number 1 and number 2 are the Lagrange multipliers. Number 1 is related to the noise of the system and can be calculated using the SNR constraint. Number 2 is used to adjust the PAPR of the signal after DPE. When we think the signal and the noise are white in frequency domain, the DPE can be expressed as the simpler formula. Here, A and B are the adjusting parameters, and A is related to number 1, B is related to number 2, and K is a gain controlling factor. This formula is more convenient for practical use. To verify the proposed method, we set up an experiment like this. We use an AWG collected with a CDM to obtain a transmitter bandwidth limited scenario. Here is the transmitter bandwidth. It is about minus 18 dB at 50 GHz. And the other parameters of the experiment are listed in this table. In the experiment, we apply the sweeping alpha method and the proposed DPE for comparison, and we measure the output power and the receiver sensitivity in the experiment. The results are shown in this figure. Here, the horizontal axis is the output power and the vertical axis is the receiver sensitivity. The red curve is the result of the sweeping alpha method. We can see that the optimal receiver sensitivity is about minus 18.2 dBm, and the corresponding output power is about minus 7.4 dBm. When we decrease the alpha, the output power increases, but the receiver sensitivity degrades. The green curve is the result of the proposed method. And we can see that the optimal receiver sensitivity is slightly better than the sweeping alpha method because it has a weak advantage in the quantization noise mitigation. And when we increase the output power of the proposed method, the receiver sensitivity also degrades, but it is always better than the sweeping alpha method. And when we consider a similar receiver sensitivity, the proposed method can improve the output power by about 0.5 dB. This result demonstrates that the proposed method can indeed increase the output power. And this figure compares the frequency response of the two methods at the optimal receiver sensitivity. As we can see, the proposed method is the green curve, has a lower response at the high frequency region, and this can decrease the PAPR of the single after DPE. And at the low and middle frequency region, the proposed method has a little higher response to maintain the performance. That's all the results, and finally I give the conclusions. First, for shorter reach coherent systems, output power and the receiver sensitivity should be simultaneously optimized. And in this work, a closed form expression of PAPI constraint is established, and a PAPI constrained DPE method is proposed. Finally, we experimentally demonstrated that the proposed method can improve the output power by about 0.5 dB without a receiver sensitivity degradation in a 96 gigabaud 32 common transmission. That's all. Thank you.
Okay, the talk now is open for questions. Any question from the audience? Yeah, either you can either.
We can see there are some questions on the chat panel.
Yeah, I see that. Yeah, so there are a couple questions in the chat window. One is that what is the time window? How many symbol derivations did you perform on the average?
Okay, for the first question, we can see here. Actually, we consider the calculating in the continuous domain, and here the capital T is the pathwise of the DPE impulse response. That means we calculate the integral at from -t to t. And for the and for the second question, you means that when the PAPR decrease, the RMS of the singular will increase. Because
so you can see the second question, right? So under PAPR constraint, is it because of electrical RMS or the available signal power has been increased?
Yeah. Because we have a peak-to-peak limited in the deck, and when the PAPR decreases, the RMS will increase.
Okay, good. Yeah, I think due to the time limitation, now we can move to our next talk. Yeah, let's thank the